which would be de-stressed or fractured as a result of the changing nature of the ground as the coal is extracted. And hence the fire damp migrates from one seam to another. They fully appreciated that. And the system that is now in place takes account of that, drains the methane from and that is an actual illustration of a methane drainage hole being drilled into the strata above the coal seam from the roadways beside the sea. And the first such system was installed in the Ruhr in 1943, 99 years after Lyell and Faraday had recommended something along those lines. And the systems now in use capture around half of the total fire damp with obvious benefits to safety, but also to the economics of mining, reducing the costs of ventilation and making some mines actually workable that otherwise might not be workable. And the drained fire damp is often used as a source of fuel for steam or gas turbines. There is a colliery at Harworth in Nottinghamshire, for example, which currently generates 20 megawatts of power from the fire damp that is drained from the mine. And an interesting aspect of the application of fire damp drainage is that the combustion of the gas significantly reduces the contribution of coal mining to global warming. Fire damp has a global warming potential which is 24.5 times that of carbon dioxide. So if you burn the fire damp, carbon dioxide and water, you achieve that a reduction by that factor. And if you take the figures for the total fire damp that is released per ton of coal and the percentage that is captured by the fire damp and burned in the drainage system, it's readily shown on the back of an envelope that the fire damp drainage system reduces the contribution to global warming from the burning of coal, that is all the coal that is extracted from the mine, by around 10%. Very significant. The second recommendation of Lyell and Faraday related to the monitoring of the fire damp in the Gulf, to make sure that the drainage arrangement that they were recommending was actually being functional and providing safe conditions. And the fire damp in the Gulf, as you can well imagine, was inaccessible to detection using the Davy lamp. Davy lamp was the only way they had at that time of detecting fire damp from the raised flame of the wick, as I have illustrated earlier. What they proposed was that the miner should introduce a copper tube into the cavity, and the tube would be attached to an air pump syringe. And this would be connected to what they call a large and sound bladder. The bladder, being carried away to a safe part of the mine, could easily have the character of its contents examined by a Davy lamp. And this suggestion, like fire damp drainage, was also lost for many years until it was reinvented by somebody else called Sir William Garforth around the turn of the century. And the particular design of lamp which would permit this to be done ever since became known as the Garforth lamp. And there you have a Garforth lamp being used in the mine. And it was used in mines until recent times. There may well be some still left. So the Garforth lamp, as you can see it here, should in truth be described as the Faraday lamp. So there you are. There is a Faraday lamp that should take its place in mining history alongside the Davy lamp. The story does not end there as far as the consequences of the Haswell explosions were concerned. Lyell and Faraday's remit was to ascertain the cause of the Haswell explosion and the reasons for the large number of fatalities. Remember, it was a very well ventilated mine. Most of the deaths were from poisoning by carbon monoxide, also known as choke damp, a product of incomplete combustion. and they concluded that this was present to a much larger extent than would have been occasioned by the firing of such fire damp as was normally present in the airways. They advanced the proposition that in fact a large volume of fire damp had been released from the Gulf by a roof fall. But in addition, and of crucial importance, they identified the burning of coal dust as a factor. And their own words provide the explanation. In considering the extent of the fire from the moment of explosion, it is not to be supposed that fire damp is its only fuel. The coal dust swept by the rush of wind and flame from the floor, roof and walls of the works would instantly take fire and burn, if there were oxygen enough in the air present to support its combustion. And we found the dust adhering to the face of the pillars, props and walls in the direction of and on the side towards the explosion, increasing gradually to a certain distance as we neared the place of ignition. Remember, they did carry out their investigation underground. This deposit was, in some parts, half an inch, and in others, almost an inch thick. It adhered together in a friable cooked state. There is every reason to believe that much coal gas was made from this dust in the very air itself of the mine by the flame of the fire damp, which raised and swept it along. And the slide that you have seen shows the cooked dust on the wooden pit props in a mine in Ayrshire in the 1950s after a coal dust explosion. And it's exactly as Lyon and Faraday described what they found at Haswell. And Faraday rapidly came to realize that the coal dust would actually take over from the fire damp as the principal, if not the only agent in propagating the explosion. In a Friday evening discourse here in 1845, he advanced the explanation, and I quote, "The gas, first of all, commences the evil, and then lights up this matter, the dust of coal, of which the whole place consists, floor, roof, walls, and every part being composed of it. The fire thus gathers energy and goes on ramifying through the mine. The ramification referred to by Faraday could be very extensive indeed. After some explosions, it is found that the flame fills several miles of the galleries. But his assertion that the gas commences the evil and thereafter by implication is not needed to ramify the explosion was not accepted in the absence of direct evidence. And the conclusion after every great explosion throughout much of the 19th century continued to be that the explosion resulted from the firing of a sudden large emission of fire damp. The evidence in favour of Faraday's belief slowly accumulated, mainly provided by careful and systematic investigation by Professor William Galloway. He first observed that great explosions only occurred in dry and dusty mines, never in a wet mine, and that the dryness and dustiness of a mine depends on the depth and the weather at the surface. But no one had been able to show that air and coal dust alone could propagate an explosion, despite many attempts at laboratory scale. There was ample evidence that even a small concentration of fire damp, less than 1% in air, was sufficient to render coal dust explosive. But this concentration was below the detection limit of a safety lamp, so there could be no certainty that explosions propagating in a dusty mine were not doing so as the result of the presence of fire damp. Now, this point was of more than theoretical importance, since sudden emissions of fire damp could be said to be inevitable, whereas the presence of coal dust was a matter of mining practice and was therefore controllable, though at a cost. And the controversy, which was fierce at times, and the language was quite fruity, the controversy was eventually settled by two pieces of evidence. The first was the demonstration by Galloway that the ease of propagation of a dust explosion depends on the scale of the apparatus used. The proof that coal dust alone could not propagate an explosion had, as I said, been derived from experiments at the scale of laboratory test tubes. And in 1882, Galloway undertook experiments funded by the Royal Society in an outdoor test rig using a duct 2 feet square and 126 feet long. He showed conclusively for the first time that a coal dust explosion initiated by a fire damp explosion could be self-supporting in air in this large-scale apparatus. And with that evidence, the views that he advocated at last began to gain acceptance amongst practical mining men, though not with the mine owners. And the event which more than any other had the effect of turning the tide of expert opinion in favour of the coal dust explanation was an explosion that took place at Altofts Colliery near Leeds in 1886. A colliery that was virtually free of fire damp. And everybody who visited the workings after the explosion agreed that the explosion was due to the combustion of coal dust alone in the complete absence of fire damp. The jury at the inquest gave a verdict in accordance with that view, and that was the first time that had ever been done. The need to take precautions was at last fully recognised, nearly 60 years after Faraday had first identified the nature of the problem. And coal dust explosions are now very rare, the last in this country being at Six Bells Colliery in Monmouthshire in 1960. Outside the mining industry, dust explosions are a recognised hazard in any industry in which flammable dusts are handled. Flammable dusts are not confined to recognised fuels, but include such materials as sugar, aluminium, and custard powder. I did say custard powder, and Jeff will now show that you have been living unawares of the dangers in your kitchen. He will blow a cloud of best custard powder. I noticed the tin simply says just add milk. Well, we're not going to add milk to it. We're going to blow the custard powder over the Bunsen burner just to show you what can happen. And it's genuine custard powder because, as you can see, Jeff has just broken the seal. So we're not using something, we haven't added any gunpowder to it. And a bit of energetic puff just to blow the dust off, and away it goes. And in the design of industrial plant handling dusts of this kind, and there are very many of them, the usual precaution is to provide means to vent the pressure generated by the explosion. Of course, there wasn't much of a bang there because there was no confinement. The pressure is vented by incorporating panels into industrial plant. These panels either fail mechanically, they're deliberately made to be weak, or they open in time to prevent the internal pressure rising to the point where the complete plant is demolished. Now, I said that coal dust explosions are rare. Well, that wasn't quite true, because there is a remote place on the moorlands outside Buxton where the HSE has a large-scale gallery which has been used for researching explosions and means for their suppression. And I have a film of an actual coal dust explosion followed by a short clip showing an industrial plant in which an internal explosion is vented through weak panels in the way that I've just described. The film begins with the coal dust being spread in the roadway, and the men who are doing it will actually convince you of the scale of the experiment. The gallery itself is 360 metres long. And the explosion is started by firing a rocket, and there is no fire damp of any kind. 3, 2, 1, 5. This is the industrial vessel. Something like custard powder in it. It's a message from your sponsor. Well, let me make that a two-explosion salute to Sir Humphrey Davy and Michael Faraday for all that they have done for us. Thank you.